Oh, good morning and happy Friday, everyone. Today we have pretty much maybe the second most important, or from some point of view, maybe the most important part of one of the most important topics in our course. We're going to look at the Gauss Elimination Method. And then we're going to look at matrix operations, in particular matrix multiplication. So actually, let's begin with the first one. So if you have two matrices that have exactly the same dimensions, so let's say you have two 3x2 matrices, you can add them together. How do you do that? By adding the corresponding entries. So 7, 3, -1, 5, 5, and 5. Okay, so we can only add matrices that have the same dimensions. The quiz was identical to a problem that we solved on Wednesday, so I don't think there is any real need to do it. It's exactly the same thing. It's in the recording. But if I have time in the end, I will go briefly over it. Okay. And you can also scale a matrix. By just multiplying each entry by the scalar. Okay. But here comes the most important one. You can actually multiply matrices and get a new matrix. However, to multiply matrices, and the order in which you multiply them is very important. In other words, compute AB, then the number of columns of A should equal the number of rows of B. So in particular, if A is n by m and B is m by k, then AB is n by k. So you see, in some sense, the middle number m, which is the same for the two matrices, disappears, and you get n rows and k columns, and the ij entry and when I say ij entry, always with matrices, the first number is the row and the second number is the column. Okay, please remember that. The ij entry of AB is the dot product of the ith row of A with the jth column of B. And of course, when I say dot product is, I mean, you multiply the corresponding numbers and add up those products. We're going to see examples in a second. So let's take a look at examples. So let's say that you have, what do you want? 3 by 2, 5, 1, 3, 4, 2, negative 2. And let's multiply it by 2 by 4, right? So 1, 3, negative 2, 4, 5, 1, 0, 2. Okay. So how do you do this? Let's do it together carefully. Okay. So I'm going to start by taking the first row. Oops. Sorry about this. Sometimes it changes between the first row of of A, of the first matrix, with the first column of B. And notice that the fact that I said that the number of columns of the first matrix is equal to the number of rows of the second matrix ensures that you have vectors that for which you can take the dot product. Because if the one had 4 entries and the other had 3 entries, you would not be able to take the dot product, right? But now you're able to take the dot product, and you have 5 times 1 is 5, and 1 times 5 is 5. So the result is 10. So this is a 3 by 2 matrix. This is a 2 by 4 matrix. So the result is going to be a 3 by 4 matrix. Okay, let me do one more. Let me do the second row with the first column, which will be the 2, 1 entry. So it will be 3 and 4 with 1 and 5, right? So it's going to be 3 times. So I'm doing this one now, just to make sure that you all see it. I'm doing this one now. And let me erase the previous one so that you can see what I'm doing. So I'm doing 3 times 1 is 3. 4 times 5 is 20. So the result is 23. Okay. Here's what I would like you to do. This matrix is going to have how many more entries? 10 more entries, right? Could you please compute them? Okay, I'll give you 1 minute. Okay, go ahead and find the remaining 10 entries so that you have the full 3 by 4 matrix. Okay, and you should do some more of these examples over the weekend. Again, look at the numbers. I said it's the dot product, so it's 3 times 1 plus 4 times 5. That's the dot product of 3, 4 with 1, 5. A good old dot product from your Calc 3 days, right? I cannot answer this question. Oh, Gauss, the name. You're asking about the name. Of course. That's the same Gauss. Okay, the one and only Gauss. I mean, we all have to know about Gauss, right? I mean, we live in a world that we know about Taylor Swift, right? And we don't know who Carl Gauss is. Honestly, you know, who is Carl Gauss? What did he do? Let's open a parenthesis for 2 minutes. Let's see if what do we know about Carl Friedrich Gauss? Yeah, so I said I'm taking 3, 4 and 1, 5, and I take the dot product of these 2 things. So look at it, 3 times 1 and 4 times 5. So first number of the row with first number of the column, second number of the row with second number of the column, right? Okay. So what do we know about Gauss? Since we're going to keep saying the Gauss elimination method in this semester, what do we know about Gauss? Gauss's law in physics, right? So in the time that Gauss lived, which is 18th century to 19th century, you didn't really have mathematicians, just mathematicians. You had people who were interested in sciences, right? So there were mathematicians, physicists, astronomers, chemists, anything you can imagine. And of course, Gauss was one of these, but you know, he's considered to be, I mean, you ask people about their top 5 of mathematicians, he should certainly make anybody's top 5. As we're going to see, the method that he devised that we're going to learn today is relevant to this day, right? It's so important. Maybe the nicest story about Gauss was when his teacher asked him, when Gauss was a 7 or 8 year old, to add the numbers from 1 to 100, thinking that nobody could do it and he could take a nap. And Gauss wrote the numbers in a very unusual way, like this. He noticed that each row added up to 101, right? And eventually he came up with a quick answer that the sum of the numbers from 1 to 100 is 5050, right? I mean, this story has been reproduced so many times, and it just shows you, if you have somebody who can do this thing genuinely when he's 8 years old, just imagine what he discovered. And what was not quite characteristic for those times is that he lived to be 80 something, okay? And he was productive throughout his whole life. Okay, so a few things about Gauss. I think you should spend a little time learning a little more. Okay. So anyhow, why don't we do the rest of the entries? I hope that you did some more. So let's do the 3-1 entry. That means third row, first column. So I have to multiply the third row. And let me, again, at least for this one, show you the rows that the row in the column that I'm multiplying, which is this one now, right? So I will have 2 times 1 is 2. 5 times -2 is -10. 2 minus 10, that's how much? How much? -8, right? Then let's do first row with second column. 5 times 3 is 15, plus 1 is 16. So that's 16. Let's do second row with second column. So that is going to be 3 times 3 is 9, plus 4, that's 13, right? I have 7 more entries, but let me take a pause. Is everybody with me? Let's do the next one. So that would be third row, second column. So 3 times 2 is 6, minus 2 times 1 is 4. And then let me do first row, third column. So 5 times -2 is -10. 1 times 0 is 0. So that's -10. Then let's do second row, third column. So that's 3 times -2, that's -6. I don't have to worry about the other product because it has the third column has a 0. And finally, 2 times -2, that's -4. Thank you. And let's do the last column now. So the last column will be 2 times 4 is 8. minus 2 minus 4 is 4. And then I have, oops, what did I do? Sorry, that's wrong. Let me try again. 5 times 4 is 20, plus 2 times 1 is 22. And then 3 times 4 is 12, plus 4 times 2, 8 is 20. And finally, 2 times 4 is 8, minus 4, that's 4. And that's it. That's the product of the two matrices. As you can see, I chose as an elaborate of an example as I could. And of course, one would ask, what are you going to ask here? I mean, there has to be a question here, right? Well, what is the question? I mean, somebody asked me last time, what are the uses of all this in everyday life? And then that's a legitimate question. I try to say that obviously linear algebra is one universal tool in mathematics, but there has to be a question here. I mean, I showed you how to multiply matrices. Many of you already knew how to multiply matrices, but there has to be a question. What's the question here? No. I'm not asking about uses. Yeah, sure. Neural networks use matrix multiplication and calc 3 through, but that's not what I'm asking. There has to be another question here. There has to be another question. The question that I'm looking for is, why in the world did we define this, right? I mean, how does one wake up one nice morning and say that if I have a matrix that has the same number of columns as another matrix has rows, then I can multiply them together in this weird way and get this other matrix? Don't you think that's crazy? I mean, who on their right mind went from not knowing what the product of matrices is to actually coming up with this monstrosity? Because it is a monstrosity. Okay, well, once you get used to it, of course, it becomes second nature. I'm not trying to scare you here into thinking that you will have trouble multiplying matrices, not at all. But why do we do that in the context of at least what we have discussed so far? And the answer is very simple. And I hope it will satisfy you that we have seen these things before. We have seen these things so far. So imagine that you have 3 vector spaces, so that you have V1, V2, and V3, and you have 2 linear maps between them. So you have the linear map T that goes from V1 to V2, and then you have the linear map S. Then you can take the composite of the 2 linear maps, that is S composite with T. And then imagine that you have a basis U on V1, a basis V on V2, and a basis W on V3. So what can you do? You can take the matrix of T with respect to the bases U and V, right? Then you can take the matrix of S with respect to the bases V and W. It turns out that the matrix of the composite of the 2 maps, so S of T, with respect to the bases U and W, is actually equal to the product of the 2 matrices. So that's one of the main ideas behind matrix multiplication. Okay? That's one of the main ideas behind matrix multiplication. So matrix multiplication amounts to taking the composite of linear maps. Okay. And as such, matrix multiplication satisfies very nice properties. So let's see. It has very nice distributivity properties. On both sides. It has a nice associativity property, assuming that all these products are possible. And I would like to emphasize the fact that there is something that I would call a non-property because it's not true. So let me write it like this. In general, AB is not equal to BA. I mean, you can find extreme examples where, for example, you take A, which is a 3x2 matrix, you take B, which is a 2x3 matrix, and then you can understand right away that AB and BA don't even have a chance of being equal because AB is going to be a 3x3 matrix, and BA is going to be a 2x2 matrix. So there's no way they're equal. But even in the case of square matrices, so the most convenient case situation is that of having square matrices. If you have square matrices, then we have what we call an algebra. So sometimes we denote it by M n by n matrices, where now we have three nice operations. So we have addition of matrices, we have scalar multiplication of matrices, and we have product of matrices. And you can even take polynomial expressions of matrices. So you can consider a cubed and a to the fourth and anything you like, pretty much, in the context of square matrices. And if you ask, are there any matrices that play the role of the identity matrix, meaning they do not change any matrix that you multiply by? This is going to be the matrix IN, which has ones on the main diagonal and 0 everywhere else. So this will be called the identity matrix. We have one for each dimension pretty much. And what is true about the identity matrix is that A times the identity matrix is the identity matrix times A is equal to A. So it doesn't change any matrix. And this will be true even if you don't have square matrices. So if you take, let's say, the identity matrix, which is, or a matrix that is, yes, they're exponents. So let me just clarify that when I say A cubed, I mean A times A times A. That would be A cubed. So if I take an n by m matrix and I multiply it by the identity with m rows and columns, then this will be A again. So the identity matrix in any scenario will always give us it will always give us the
excuse me, what's IM?
The same matrix. I'm sorry?
Is IM is the identity, it should to be the same identity, or what's IM should to be?
Exactly, because I have m columns for A. To have a possible multiplication on the right, I need to have the identity matrix that has m rows and m columns.
Can you give example of that?
So what I mean by this is if I had, let's say, a 2x3 matrix, so then the identity matrix that I should put next to it is the 3x3 identity matrix, because otherwise I wouldn't be able to multiply them. That's what I mean. So this was 2x3. So this has to be the 3x3 identity matrix, so I3.
Thank you.
Any more questions, please? And to believe me that matrix multiplication is not commutative, why don't you do a quick example? Please compute 1, 2, 4, -1 times 2, 3, 1, 5, and then compute 2, 3, 1, 5 times 1, 2, 4, -1. Please go ahead and do this computation. Can anybody tell me row by row what is the first matrix? Four, 13, 7, and 7. Do we all agree? And again, row by row, what is the second matrix? Second matrix.
$13, 1, 21, -1, or -4.
13, 1, -21, you said?
Just 21.
Okay, I'm hearing different things here. So I see two, this is 14, 1. Definitely, this is 14, 1. And then what is the second row? 21, -3. Okay, do we all agree? The bottom line is that they're different. Okay, the bottom line is that they're different. Okay. Before we do our next thing with matrices, let's catch our breath and take our attendance. Please send me the word Gauss for your attendance. 30 seconds, please, as usual. Okay, don't want to Don't send it to me. Send it to everyone. Somebody, I think Al, you send it to me. Send it to everyone, please. Because these are the messages that are recorded. It's Gauss, not Gauss. Again, Tony, it's Gauss, not Gauss. It's yeah, I think you might think to yourselves that it's but none of us wants to have their name misspelled, right? Take it from a person whose name is misspelled all the time. So somebody's asking me to check the 13 that we got. So let's check it. So it's going to be 1 times. So what is that number? That should have been this times this, right? So it's 1 times 3, which is 3. 2 times 5 is 10. 3 and 10 is 13. So it's correct. Okay, to get this one. Great. I'm glad you're asking these questions. And please redo these examples at home. Finally, I would like to introduce one more thing regarding matrices, which is the inverse of a matrix. So if A is an n by n matrix, and B is an n by n matrix such that AB is the same thing as BA and it's equal to the identity matrix, then A is called invertible and B is called the inverse of A. It is denoted by A to the negative 1. Not every matrix is invertible. We're going to learn very, very well which matrices are invertible. And I'm going to give you a good reason why we should know how to find inverses of matrices. Generically, every square matrix is invertible. So when I say generically, I mean that it's harder for a matrix to be non-invertible than to be invertible. So most matrices are invertible. If a matrix is not invertible, then it is called singular. If a square matrix is not invertible, then it is called singular. So we have quite a bit of terminology here. So we talked about invertible. Oops. Let's try again. So we talked about invertible matrices, about the inverse of a matrix. Square, we call it square matrix, not squared, square matrix. And singular matrices, okay? Yeah, so the only matrices that qualify as being tested, whether they are invertible or not, are square matrices. So if you have another matrix, don't even think about asking whether it's invertible or not. Okay, that's the bottom line. Can I do an example? Oh boy, let's see if I can find an example on the fly of the inverse of a matrix. So let me give you something like 4311. Okay, let's see if I can play with the entries, right? So a to the negative 1 let's see if I can guess it right. So, oops, a to the negative 1 will be, is it 1, negative 1, and then you're saying negative 3 and 4. I think you're right. Let's see. No, this doesn't. Does it work? Yeah, I think this works. Okay, there you go. That's a simple example. Okay, so if you multiply them, you will find the identity matrix, the 2 by 2 identity matrix. One of the reasons why, but like I said, the main reason was the composition of linear maps. However, there's another very nice thing about products of matrices that makes our life very nice here, is that if somebody gives you a system, let me put some negative numbers too. Okay, if somebody gives you a system, you can write it as 3, 4, 7, negative 5 times the column matrix xy being equal to 2, negative 1. This will be called the matrix of the system. Matrix of the system. And there is another matrix which is going to be relevant in our discussion, and it's the matrix where we also attach the column of the constants. So this will be called the augmented matrix of the system. Augmented matrix of the system. Okay. So the matrix of the system and the augmented matrix of the system. Okay. And pretty much the idea here is that you have a matrix A, let's call this A, let's call this X, and let's call this B. Yeah, it's a different way of writing, but all of a sudden the system is written as a matrix equation. So this is the system, and this is a matrix equation. And sometimes people like to think that they can find an inverse for A. So if hypothetically you could find an inverse for A, then you could say a to the negative 1 times ax is equal to a to the negative 1 times b. So you multiply both sides by a to the negative 1. And this will become in times x is equal to a to the negative 1b, which means that x is equal to a to the negative 1b. In most cases, I would like to say that we do not solve systems this way. We do not solve systems this way. Okay. Okay, let's take a break. And when we come back from the break, we're going to do the one and only Gauss elimination method. So I want you at your best when we come back from the break. Okay? Okay. So see you in a few minutes. Okay, so as we said, we're going to look at the Gauss elimination method now. And are there any questions on what we did during the previous hour?
Is there a property that undoes a dot product?
What exactly do you mean by that? A property that undoes.
You know how like in arithmetic we have division, which is like the reverse of multiplication.
Mhm.
So is there something like the
Mhm.
reverse of
No.
dot product?
For the following simple reason, because when you take the dot product of two vectors or two matrices, one column matrix, one row matrix, one column matrix, the information that you get is very, very minimal. You get just a number. So you could have a row of 100 numbers, a column of 100 numbers, and the result will be just one number. It will be very hard to just use that number and some reasonable amount of information like a row of 100 other numbers in order to get what you had before. So the quick answer is no.
Okay.
Any more questions, please? So let's talk about the Gauss elimination method. The idea is very, very simple. The idea is that if you have a system, any system can be encoded using matrices. So the question is, what does a matrix have to look like so that you can solve the system right away? And the answer is the following. In general, you want a matrix to look like this. And I'm making it, let me make it a little more specific than, so imagine that I have an augmented matrix. So this is supposed to be an augmented matrix. And it should look like this. Let's say 1, 2, -1, 5. 0, 1, 2, -3. So let's say that it looks like this. Okay, so this is hidden behind what system? What would be the system that corresponds to this matrix? And the answer would be x plus 2y minus z is equal to 5. And y is plus 2z is equal to -3. Do you agree? Augmented matrix means the matrix where we also attach the column of the constants on the other side. Remember, I gave these definitions. Let me go back where I gave those definitions. Right here. So you see, this was the system. This is the matrix of the system right here. And the augmented matrix is where I have also the numbers on the other side, as you see. So I have the full information of the system. Unfortunately, the matrix of the system doesn't involve the columns, the column on the other side, but the augmented has all the information. Okay. Whenever you apply the Gauss elimination method, you will always work with the augmented matrix. Always. Okay. So my claim is that this system is ready to go. Why? First of all, as you're going to see, we're going to call these entries pivots. And even though pivots do not have to be equal to 1, they could be any non-zero number. To make our life easier in this course, I will always assume that they're equal to 1. They have the following property. They are the leftmost non-zero entries of the row. So pivots are leftmost non-zero entries of the row, and everything underneath them is 0. In particular, if you have this kind of configuration where pivots of high rows are on the left of pivots of lower rows, and every row either has zeros or has a pivot, then we're talking about the row echelon. It's called a row echelon form. Row echelon form. And basically, I claim that once you have a row echelon form, you can solve the system. I claim that you can solve the system. And let me show you how. Let me show you how. So for this system, for example, the principle that we're going to use from now on is that if a column does not have a pivot, then it corresponds to 3 unknowns. A pivotal element, it corresponds to a 3 unknown. And you always solve it from the bottom to the top. So here, I would just take y to be -3 minus 2z. So I solve the last equation for its pivotal element. And then I plug it into the second one. And I solve that for x2. So I will get -4z minus 5z. So I will put it on the other side as 5z. And I will also have -6, put it on the other side, plus 5, that will give me plus 11. And this is the solution. And z is free. When I say free, it can be any number. It can represent any number. Okay, and that's the solution. Let's do one more. Let's do one more. I will give you the solved system. So when you have the row echelon form, that's when the system has been solved. And then I'll show you how to bring it to the row echelon form. So do this one, please. Let's not start with 0. Keep changing my mind. Do this one. Okay, and always think, sometimes you can see the dotted line, but in most cases, please understand that I will be omitting the dotted line. So try to solve this system. Try to write the system which is hidden behind this matrix and then solve it, please. Okay, let's see together. So we have x plus 2y plus 3z is equal to 5. And then z is equal to 2. So can anybody tell me what will be a free unknown here? Or first of all, let's say what the pivotals are. What are the pivotal elements? Are pivots on the matrix. This, why? Because it's the leftmost non-zero entry, and it's equal to 1, and everything below it is 0, and this one. So these are the pivotal elements. Which one doesn't have a pivotal element? This. No pivotal. So y will be a free unknown. Y will be free. You know that from the beginning. So how do you solve this? The last equation is already solved. Then you plug it into the first and you get x plus 2y plus 3 times 2 is equal to 5, which gives you x plus 2y is equal to -1. And you solve for x and you have -1 plus 2y. So here's your solution, and y is free. Let's do one more. Let's do one more. And here's what another thing that you might get. Here's another thing that you might get. This is another thing, another possible situation. And this is a very special situation. So write it down and try to see what we're getting here. This is pretty much the simplest one to handle, but we have to be careful on what we say here. Like I told you, this is an interesting one. Yes, z will be, yes, it is tricky. But when you write it out, it will be rather revealing, because look, the first equation is not hard to write, right? The first equation will be x plus 3y plus 5z is equal to -2. So no problem here. The second equation will be xy plus 2z is equal to 2. But I hope you did scratch your heads about the third equation, right? There's something wrong with the third equation. What is the third equation? Can anybody tell me what the third equation should be? Right, that's what it is. It's 0 is equal to 1. And you know what? It's fine if you write 0 is equal to 1, or it's fine if you write 0x plus 0y plus 0z is equal to 1. No matter how you write it, the conclusion is the same. The last equation is impossible. Okay, so this system has no solution. No solution. We don't worry about free unknowns or anything like that. What 0 equals 1 means it's really this thing. And this is impossible. There's no way you can add 0x plus 0y plus 0z, no matter what x, y, and z are, and find 1. This is simply impossible. Okay, so here we say that the system has no solution. Okay, so now it's time to tell you how to bring it to row echelon form. And this is where we're going to present the Gauss elimination method. And the Gauss elimination method must be one of the cleverest methods that you can ever find in mathematics, or maybe in all sciences. And that's why I told you that it's pretty much the same as it was in the time of Gauss. And the idea is like this. Start with any matrix. So I start with any matrix. 1, 3, 5, 2. 2, 1, 1, 3, 3, -2, 1, 0. So I start with a generic matrix like this. Okay. I start with a generic matrix like this, and we're allowed 3 types of row operations. We're allowed to perform 3 types of row operations. We will call them row operations. The reason we are allowed to perform these 3 types is because if you translate them into operations on equations, you will see that you keep getting equivalent systems, meaning the systems may change on how they look like, but they have the exact same solutions. So what do they look like? What are the 3 operations? So the first one, and the most important one, is add a multiple of one row to another row. I will have a way to denote this. So I will say, for example, -5 row 1 plus row 2. And I will mean that this is the row to be added. More precisely, a multiple of that row. And this is the row we're adding to. Please understand that in some sense, when I say add a multiple of one row, I really mean of the copy of one row, meaning the row itself is going to stay exactly as it is. Let me do an example. So let's say I have 3, 1, 2, 6, 4, 5. Let's say I have this, and I want to perform, as I said, -5 row 1 plus row 2. What am I supposed to do? First of all, I don't write equalities. I just write the matrix. Again, I'm not saying the matrices are equal. I'm saying I'm going from the one matrix to the other by this row operation. And so row 1 remains as it is. It's 3, 1. 4, 5 will also remain as it is because it's not even part of this operation. The only thing that will change is row 2. And how will it change? I need to multiply every entry of row 1 by -5 and add it to row 2. So -5 times 3, that's -15, plus 2, that's -13. And -5 times 1, this number 1, right? Oops. What did I have here? Did I have a 6? I think I had a 6. I had the 6, right? Okay, so -5 times 1. When I say 1, I mean this number 1 times plus 6, that will be 1. And there you go. So that's the first row operation. The second row operation is very simple. Multiply a row by a non-zero number. You don't want to multiply by 0 because then you eliminate information. The nice thing about the row operations that we explained here, all of them are reversible. Somebody asked me before whether the result of the dot product is reversible, whether we can recover the rows that we have. And the answer I said was no, in at least a simple context. But here, everything that we do is reversible. So we would denote it like 4 times row 2. 4 times row 2. And it would be what? Let's say if I have this matrix and I want to perform 4 times row 2, I write it next to the matrix. Again, I don't write equal. 4 times 5 is 20. And 4 times 6 is 24. And the last operation is swap two rows. Swap two rows. This is very, very simple. So let's say you want to swap row 2 with row 3. I'm going to denote it like this. Let me give you a quick example. 1, 5, 2, 3, 1, 6, negative 2, 1, 7. And I want to swap row 2 with row 3. This will be as follows: 1, 5, 2, negative 2, 1, 7. So row 2 becomes row 3, and row 3 becomes row 2. And that's all. And my claim is that by using these operations the right way, I can actually bring my matrix to row echelon form. And I plan to show you this for this particular matrix. Are there any questions before we execute the Gauss elimination method? The idea is simple. Start with the leftmost column. Create a pivotal element, and then use that pivotal element to eliminate everything below it. When I say eliminate it, make it equal to 0. Here, I'm all set. I start with the first column, and I see that my number is 1. If the number was 7, I would simply multiply the first row by 1/7 so as to make it equal to 1. Okay, so I would use the second row operation. But it's equal to 1, so what do? First thing is, I want to eliminate, my goal is to eliminate this number, 2. I want to eliminate this number. So I'm asking myself, what number should I multiply 1 by? So when I add it to 2, I should get 0. What number should I multiply 1 by? So when I add it to 2, I get 0. And the answer is, the answer will always be the opposite of the number. So guess what row operation I declare? I declare minus 2 row 1 plus row 2. And then I execute. So 1, 3, 5, 2 and 3, negative 2, 1, 0 remain the same. And the middle row will be what? Negative 2 times 1 plus 2, that's 0 as I wanted. Negative 2 times 3 is negative 6 plus 1 is 5. Sorry, it's negative 5. Negative 2 times 5 is negative 10 plus 1, that's negative 9. And negative 2 times 2 is negative 4 plus 3, that's negative 1. Any questions, please? So can anybody guess now the next step? What is the next step? Can anybody tell me in terms of row operation? Tell me what row operation I want to do next and why. That was the type 1, meaning I am adding a multiple of one row to another row. So I gave you 3 types of row operations. I just used the first one.
You can multiply row 2 by negative 3/5.
No, you will always use your pivotal one. You will not touch row 2 again in this cycle of things. So I will multiply again. No, it's not row 2. Row 2 cannot have the effect that I like on row 3, right? Because now the first entry is 0. So what will I do? It will be minus row 1, minus 3 row 1 plus row 3. Okay, you will always be using your pivotal element to eliminate everything below it. So 1, 3, 5, and 2 stays as it is. 0, negative 5, negative 9, negative 1. And then minus 3 times 1 is minus 3 plus 3, that's 0. Minus 3 times 3, that's negative 9, minus 2, that's negative 11. Minus 3 times 5 is negative 15 plus 1, that's negative 14. And minus 3 times 2 is negative 6 plus 0, that's negative 6. Okay? And basically, what I want you to understand is that when you're done with a column, you're not going to touch the column and the row again. So from now on, everything we do will be with this part. You're not going to touch the row and the column that you just used again. Okay, and that will make your life very easy. So now I need a pivotal element. I have this ugly negative 5. So there are other ways to do this, but I will go with the simplest one for the moment being, which is going to introduce fractions, of course. I'm going to make this pivotal with my definition of pivotal. So negative 1/5 times row 2. Why? So that I make this equal to 1. Okay, so what do I get? I get 1, 3, 5, 2, 0, 1, 9 over 5, and 1 over 5. And then I get 0, 11, I'm sorry, negative 11, negative 14, and negative 6, right? And now I need to eliminate one of them. Which one do I need to eliminate? This one, whatever lies below my pivotal one. So how am I going to eliminate this? Can anybody tell me how I'm going to eliminate this? 11, why do you say row 3? It's 11 row 2 plus row 3. The pivotal now is in row 2. Okay, excellent. So 11 row 2 plus row 3. And what do I get? I get 1, 3, 5, 2, 0, 1, negative over 5, 1 over 5, 0. This will become 0. And now it's 11 times 9 over 5. That will be 99 over 5. I need to bring minus 14. I need to write this with denominator 5. It's going to be negative 14 times 5 is negative 70. So I have 99 plus 70. That's 29 over 5 is going to be here. I hope I'm not making any mistake. And last one, it will be 11 over 5 minus 6, which is 11 over 5 minus 30 over 5, 11 over 5 minus 30 over 5, and that will be minus 19 over 5. Okay, so now I'm done with the second column. Okay, so now second column, second row, I leave them behind me. I'm not going to touch them again. And what do I get? I get, I'm going to work with this. I want to make this 29 over 5 pivotal. So I will multiply 5 over 29 times row 3. And it's 5 over 29. So the inverse, not the reciprocal. 1, 3. Yeah, you see, that's the point that I made. In many cases, you will see, in many places, you will see that you're told that it doesn't have to be equal to 1. I will insist in this course that we make them equal to 1. Okay. Pivotal ones. So 0, 0, 1, and this will be negative 19 over 29. So now we're in business. Now we have row echelon. So this is row echelon. If we want, we can go ahead and solve the system. This system will have a unique solution. But pretty much what I want you to see is that we have our pivotal. What are our pivotals? This one, and this one, right? They're, in each case, they're the leftmost entries and everything, the leftmost non-zero entries. And they're lined up so that lower rows have their elements, their pivotal elements on the right of high rows. And thank you for solving this to us. I did not intend to solve it, but thank you for doing that. So the solution was just found. But as I said, our goal here is to bring this to the row echelon form. And there will be many interesting cases, and you will see that we'll use, I'll use this method on video for different reasons. Like maybe 50 times till the end of the semester. Okay, so the Gauss elimination method will become our bread and butter. So we'll be doing pretty much from this day forward, we'll be using this method over and over and over and over for many different things. But I really want you to take a few matrices and try to apply the Gauss elimination method the way we showed. And we're going to do more examples on Monday. Okay. Yes.
Why you use such as a column method to solve that? Why you don't go to such as a row? So instead of making 1 0 0 for the first column, why you don't go directly to make the -5 to become 1 instead of going to the third row?
I'm sorry.
Okay, when you use this method, you try to make the first column to be 1 0 0.
Right.
Why you don't go to make the second row first, such as changing the -5 to become 1 first, and after that going to the third row to solve the situation to be 0 0 and 1?
No, not 0 0 and 1. The leftmost entry has to be the last entry at this point has no hope of being 1. So it's going to be the third entry that's going to be 1. Okay, that's how the pivotals are going to be. Because pretty much you will always work with the first column, right? And once you have worked with the first column, you will do the same thing to the part that remains. Okay, what I did was very much, so what I did at this point right here is exactly what I did at that point. So my method has been very, very consistent, and that's one of the goals that I try to establish here, that what I'm going to be doing is going to be very, very consistent in each step. Okay?
Thank you. Thank you.
So could we find variations here? Could we do less? No, I doubt that we can do less. Could we do a little more? I will tell you later how. So we will talk at some point about a reduced row echelon form. So today, what we established was the row echelon form, and in some books, the only difference that you will find is that there is not a requirement for the pivotal elements to be 1. I do want them to be 1 so that it's easier for us to mark them and have uniformity in what we do. Okay. We will work a lot more with this method, but please make an effort to at least work out this example that we just did several times over the weekend. And then we will discuss things again on Monday. I wish you a very, very nice weekend. Don't forget to submit your homework tonight early, always. And I will see you on Monday.
Thank you.